Let us now discuss, student, non-stoichiometric defect. Non-stoichiometric defect. So I have discussed in my previous video about stoichiometric defect. So I told you about stoichiometric compounds, that those compounds which have same number of positive and negative charges that should be present in its formula. But in non-stoichiometric it is just vice versa. There will be change in the number of cations or anions that should be present in the formula. The compounds in which the ratio of positive and negative ions present in the compound differs from that required by ideal chemical formula of the compound are called non-stoichiometric compounds. एकदम सिंपली हम लोग कह सकते हैं स्टूडेंट कि वैसे कंपाउंड्स जहाँ पे नंबर ऑफ कैटायंस और एनायंस जो होने चाहिए थे फार्मूला के अकॉर्डिंग वो नहीं है, तब आप उसको नॉन स्टोइचियोमेट्रिक कंपाउंड्स कहते हो. जैसे मैं एक सिंपल सी एग्जांपल ले लूँ यहाँ पर स्टूडेंट. लेट मी टेक एन एग्जांपल ऑफ निकल ऑक्साइड. सो द फार्मूला ऑफ निकल ऑक्साइड इज NiO. So what we see here, that nickel is 1 in number and oxygen is 1 in number. 1 atom of nickel, 1 atom of oxygen. But if this defect arises here, student, there will be change in the number of cations, or it could be anions also. So now if this defect arises here, now just check what happens. We have same number of anions, no problem. But the number of cation is less here. It should have been 1, but it is 0.98 less number of cations. So this is non-stoichiometric compound. This is non-stoichiometric compound, and the type of defect in such non-stoichiometric compound is called as non-stoichiometric defect. So this non-stoichiometric defect could be of two types, student. Metal excess defect, and B will be metal deficient defect. Now let us first go through metal excess defect. So in these defects the positive ions are in. So what should be here? I have written here a blank, student. So what should be in this blank? Metal excess means cation should be more. So in these defect the positive ions are in excess. Positive ions are in excess. Okay. So this could be due to two reasons. Just check out these reasons, students. The first reason is when there is less number of anions due to anion vacancies. So if there will be less number of anions, certainly there will be more number of cations. So metal excess. So let me draw this, student. We have A plus cation, A plus as cation, B minus as anion, B minus, here it should be B minus, this is A plus, then there should be B minus. I am not writing here because anion vacancy, anion is not there. Okay, so here this is A plus, here this is A plus, here this is A plus, here this will be A plus, and here it is A plus. Here this is B minus, B minus, B minus, B minus. This is ionic. For case of ionic solids we have. So student, just check this out. What is happening here? We don't have B minus. Here is anion vacancy. Now how you should first know that how this anion vacancy is created. How this, you can see here that this is anion vacancy, but how this anion vacancy is created, you should know it first, and then we will work ahead, student. So in this case negative ions may be missing. You can see here negative ions missing from their lattice sites, leaving behind holes. So when there is no negative charge, hole is created in which the electrons remain entrapped. This region will be trapped with electron to maintain the electrical neutrality. Obviously we are discussing the case of ionic solids. an ionic solid should be electrically neutral, meaning thereby the number of positive charges should be equal to number of negative charges. We have one less negative charge here. So in order to maintain this negative charge, in order to maintain the electrical neutrality, student, there should be presence of a negative charge here, and here electron is entrapped. Here we have electron, student. This is electron. Now some question arises here that where B minus has gone and from where we have got this electron. These are the questions here. So let us go through these things one by one. Okay, so you should know that this defect arises in case of metal halides, alkali metal halides. Keep this thing in mind, student. This defect arises in case of alkali metal halides. Okay, and these defects are likely to be in compounds which shows Schottky defect. You should also remember this thing, that this defect is likely to be in compound which shows Schottky defect. It arises in alkali metal halides. For example, I have written here many things, but let me clear this thing. So student, what I have written here, I must tell you, I have got, let us take sodium chloride as the alkali metal halide, NaCl. Okay student, let us take sodium chloride as the alkali metal halide. Just a second. So I have taken sodium chloride NaCl as the alkali metal halide, Na plus Cl minus. Now students, if I draw the lattice positions, if I draw the lattice positions, what I have here will be the Na plus ions and Cl minus ions. So here I have Na plus ions, here I have Cl minus ions, Na plus ions, Cl minus ion, Cl minus, Na plus, I am not writing here Cl minus, then Na plus, Cl minus, Na plus, Cl minus, Cl minus, Na plus, Cl minus and Na plus. Now here we don't have Cl minus, this is the anion we can see. Now what happens student, when we heat sodium chloride in its own vapor of sodium atom, when a metal halide is heated in its own metallic vapor, so when we have heated sodium chloride in the vapor of sodium, what happens, ionization of this sodium atom takes place, Na plus plus 1 electron ionization takes place. Okay, so when we heat this NaCl, this metal halide, this Cl minus ion, chloride radical, okay, chloride radical moves from its position and it goes to the surface of the solid to interact with the Na plus ion. Okay student, I think now it is clear. So where is this Cl minus ion? This Cl minus ion has gone to the surface to interact with Na plus ion. So we have a vacant site. Instead of Cl minus ion, we have a vacant site here. And how this vacant site has created? Because this Cl minus has gone to the surface to interact with the Na plus ion, which has formed due to ionization of this sodium atom. And these released electrons in the ionization of this metallic sodium, the released electrons are trapped in this vacant site. Here this vacant site we have electron, and this electron, released electron, is trapped here students, so I will represent here electron. Okay, so this is very clear that this Cl minus ion, anion, has gone to the surface to interact with the cation which is formed due to the ionization of the metallic atom, and the released electron in the ionization gets trapped here. So this is what I have written here student. This is what I have written here, whole about what I have just discussed here. Okay, you just go through this detail. You can capture it also. You can take a snapshot and capture it also. Okay, now the electrons trapped in anion vacancies are called F center. This center, here we have an electron, student. This electron, this center is called as F center. F center. F is Farben center, student. F stands for Farben center. It's a German word which means color center. Color center. This electron, trapped electron, is responsible for color in metal halides. So how it is responsible? So when it gets heated, these electrons starts vibrating and it releases energy. These vibrating electron releases energy. Okay, and when these electrons from higher excited state falls down, okay, then we get color of that particular metal halides. So these centers are responsible for color in metal halides. This electron gets vibrated when it gains energy and it releases energy of certain radiations, and thus colors are imparted by these metal halides. So due to excess of Na plus ions in sodium chloride, if we have more number of Na plus ion, meaning thereby we are talking about less number of Cl minus ion, it is yellow in color. Why sodium chloride gets yellow in color when heated? Because of this F center, Farben center. Due to excess of Li plus ions in lithium chloride, it is pink in color. And due to excess of potassium ions in potassium chloride, it is purple in color. It is purple in color. Student, in the next video, I will discuss metal excess defect due to excess cation.